Hello, my name is Prabhu, and today I want to tell you about our new paper titled An Axion Pulsarscope. This is work in collaboration with Mariia Khelashvili, Mariangela Lisanti, and Ben Safdi. In our paper, we propose a new target for axion detection experiments. Previous axion detection experiments may be classified by the source of axions to which they're sensitive. For example, haloscopes are sensitive to axion dark matter. Light shining through walls experiments are sensitive to axions produced in the laboratory, and helioscope experiments, such as CAST, are sensitive to axions produced in the sun. In our paper, we propose a new class of candidates known as pulsarscopes, which are sensitive to axions produced by nearby pulsars. Some of the advantages of a pulsarscope include the fact that pulsars may produce highly coherent axion signals, with coherence times exceeding even those of axion dark matter signals at the same frequency. These axion signals may also be relativistic, which could aid in experiments sensitive to the axion spatial gradient, as I'll discuss in a few slides. And these signals lie at the known rotation frequencies of pulsars, which makes searching for them much easier than searching for signals of unknown frequency. And finally, this story does not assume that axions make up a significant fraction of dark matter. They only rely on the existence of axions in a particular mass range. So now the question is, why pulsars? So pulsars, which are rapidly rotating neutron stars, have some of the largest electric and magnetic fields in the universe. This is particularly convenient for axion searches, since axions couple to electromagnetism through this FF dual or E.B operator. Pulsars also have extremely stable rotation periods, which make them good astrophysical clocks. They're also very abundant and may be quite proximate to Earth. So now I want to talk a little bit about how we estimate axion signals from pulsars. So pulsars are generically expected to possess gap regions in which E.B is unscreened. As I mentioned in the previous slide, E.B can be treated as a source for the axion field. We consider two models which are meant to bracket the astrophysical uncertainties in axion production. In the optimistic case, the entire magnetosphere of the neutron star is unscreened. This is the so-called vacuum dipole model, in which the neutron star is treated as a spherical conductor bathed in a large dipolar magnetic field that is misaligned to the rotation axis with an angle theta m. And in the vacuum dipole model, we can compute the power, and we get something like this down here. In the pessimistic case, almost the entire magnetosphere is screened due to the presence of electron-positron pairs. However, the screening cannot occur everywhere. For example, small localized regions near the magnetic poles of the neutron star will have an unscreened E.B, which may source axions. These small regions can be treated as point axion charges that rotate around this axis with frequency omega, giving off an axion power that looks a lot like the Larmor radiation of a rotating point charge. So once we've produced this axion power, this leads to a signal on Earth, which looks like this. This also depends on, in addition to the power and the frequency of the pulsar, it depends on the distance to the pulsar. So we do expect these signals to be quite weak, but as I mentioned, there are a number of advantages that make these searches easier than, for example, a dark matter search. So in our paper, we looked at the sensitivity of various upcoming axion dark matter experiments, such as dark SRF, Casper, and DM radio gut. And as I mentioned, searches for pulsar-sourced axions benefit from the large signal quality factors and an enhancement in the spatial gradient, since the axions produced may be relativistic compared to axion dark matter, which has non-relativistic axions. Just to take a look at our results, we see that dark SRF may probe new parameter space, improving upon existing astrophysical constraints, assuming the Crab pulsar and a vacuum dipole model. However, assuming the pessimistic model in which most of the magnetosphere is screened, we see that the projections, even with future axion detection experiments, are subdominant to helioscope experiments like CAST. A similar story arises in CASPER, where vacuum models for the Crab pulsar may probe new parameter space that has not been explored by astrophysical probes. But in the pessimistic case, the projections are subdominant. So this motivates better magnetospheric modeling to understand where the true line between the optimistic and the pessimistic case lies. It also motivates additional searches for better candidates, such as younger pulsars and pulsars arising from future supernovae. Additionally, we may expect to look for transient signals from pulsars, such as those associated with flares or glitches. And finally, a related idea searches for axion emission from binaries, such as neutron star, or neutron star black hole binaries. And the promise of pulsar-sourced axion searches motivates adding axions to the vibrant multi-messenger astrophysics program. So thank you for your time, and I hope you take a look at our paper. Please reach out if you have any questions.